Okay, so good evening everyone and welcome to week 11 of this tutorial session. So am I audible to everyone? Okay. And the screen is also visible? Okay, so let's start today's session then. So have you gone through all the video lectures of week 11? Okay. So based on whatever you have learned in this week, that is the Nyquist plot or the phase margin, gaze margin, or we can say about relative stability. So based on those topics, we are going to solve some questions, some basic questions, and then if there is some time, we will go to some advanced questions on these topics. Okay, so before that, in the previous week, I have given you one question to solve. So, yes. So, this question I given to you. So, anyone try? Anyone is able to get the transfer function of this question? Okay, so let's start by solving this question only. Okay, so in this question you were given the asymptotic approximation, that is, which is nothing but the approximate magnitude Bode plot of a transfer function, and it is given that you have a minimum phase system and all the poles are real and you have 1 0. So for this you have to find out the transfer function. Okay, so how to proceed for this question? Now by looking at the Bode magnitude plot, can you guess the corner frequencies and the type of the system? First tell me what is the type of system? What is the initial slope of the Bode plot? It is minus 40 dB. Yes, since we have an initial slope of minus 40 dB, so minus indicates that there is a pole, and initial slope of 40 indicates that we have a pole at the origin, and minus 40 indicates that we have two poles because one pole contributes a slope of minus 20. So since there are two poles, so they are contributing for minus 40 dB per decade of slope. Now type of system, we are sure that it is a type 2 system. Now tell me what are the corner frequencies? So type of transfer function is 2. Okay, and let's calculate the corner frequencies. So what are the corner frequencies? If you write in time constant form, the corner frequencies are nothing but 1 by t. Okay, so corner frequencies are, we have 2, 5 and 25, right? So the slopes are changing at omega 2, 5 and 25. Okay, so the corner frequencies are 1 by 2, So these are your T. So corner frequencies are 2, 5 and 25, and T1, T2 and T3 are this. Now at omega equals to 2, can you guess whether there is a pole or 0? The slope is changing from minus 40 to minus 60 dB.
Pole.
So there is an addition of minus 20
Pole.
dB of slope. So there is a pole. Okay. So there is a one pole here. Okay. What about omega equals to 5?
Or zero.
There is an addition of plus 20 dB per decade. So there is 1 0. And similarly at omega equals to 25, we have an addition of
One pole.
pole. So there is a one pole. So what we can write? We have a transfer function of the form k by s square, because it is a type 2 system, and then we have one pole at 2, so we have 1 plus st1, and then we have a 0, so we have 1 plus st2, and then again a pole, so 1 plus st3. Okay, so this is the form of transfer function. Any confusion?
No.
Okay, so we can write it as k into 1 plus s by 5 divided by s square 1 plus s by 2 and 1 plus s by 25. Okay, now the only thing which is left is to calculate k. How can we calculate k? By looking at the initial value, and initial value is given at omega equals to 0.1. Okay, so what we can write about the magnitude? So initial magnitude is given by okay, since all these are poles and zeros have 0 dB asymptote, 0 slope at the initial frequencies. Okay, as omega tends to 0, they contribute for 0 slope. So only contribution is coming from k and 1 by s square. So the initial magnitude can be written as 20r. R is the number of poles or zeros at the origin. Omega naught is the initial frequency and k is the gain. Okay. Now what is r in this case? R is 2, and we have slope here, so we will use a pole here, so it is minus 20 into 2. Initial frequency is given as 0.1, and minus 20 log k we have to identify, and this value is given as 54. Okay, so what we can write for this? So this is 0.1, it will contribute to negative sign, so we will have 40 log 1, which will go to 0, minus 20 log k.
Did you write plus 20 above that?
Sorry, oh sorry, it will
Plus
be 10 to the power minus 1, it will not go to 0. It will be minus 40 log plus 40 log 10 minus 20 log k is to 54.
plus 20, you write in the first step.
Yes,
This plus minus 20 are log omega 0 plus 20 log k. So
this
in
sign,
next step also
this sign you are
above
talking.
above step.
Your voice is not clear to me. Can you please repeat what you are saying?
First step I am saying.
Yes, here.
Yes, this
Hmm.
plus sign in between. So in next step also.
No, no, no. I am saying plus or minus. So that depends on the slope or the pole or zero. If you have a zero at the origin, you will use plus sign because that contributes for positive slope. And if you have a pole at origin, you will use minus sign because you have a pole at the origin. So in our case, there is a pole at the origin because it is a type 2 system, and also in the border plot you can see you have initial slope of minus 40. Okay, so that's why we are not
Because
using plus sign but minus sign because we have pole at the origin, so that contributes
this
for
sign,
negative slope. Yes,
the sign previous to 20 log k, I am saying.
this sign.
Yes,
So what is the magnitude of k in dB? It is 20 log k, right? It is in
yes,
numerator, so its magnitude is just 20 log k, so that's why we have written 20 log k plus 20 log k.
yes,
Okay, clear?
yes.
So let me write it clearly. It is plus. Okay, now you can easily calculate for k.
Then in next step, how you change the sign
Oh, no,
plus
no,
to
no, no,
minus?
no, 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 no. That's a mistake. It is plus.
That was the point.
It is plus. It is plus. So it is 54 minus 40 will be 14. The log k will be 14 by 20 will be around, not around, it will be equal to zero point 0.7. Then your k will be equal to 10 to the power zero point 0.7. Zero point 0.7. What is 10 to the power zero point 0.7?
5.01.
So it is almost 5. Okay. So your final transfer function will be equal to 5 into 1 plus s by 5, 1 plus s by 2, and 1 plus s by 25. So many times you will see options where these are written like this. So it will be 5 s plus 5 by 5 s plus 2 by 2 and s plus 25 by 25. Okay, so it will be 50 times of s plus 5, s plus 2. Okay, where positive coefficient, in which step? Here, here it will be positive only. By mistake I earlier written minus. It will be positive only because what is the magnitude of k? Because you have k by s square only, which is dominant at the initial frequency. So its magnitude will be 20 log k minus 40 log omega. So it will be positive only. Is it clear?
Yes.
Okay. So this was the question that I asked you to solve. Okay, now let's move to this week's questions. So start with very basic problem. So here you are given a unity negative feedback closed loop system whose open loop transfer function is this. You have to just find out the open loop poles. So this is very basic. Please tell me what are the open loop poles. Okay, before that, there is okay, Shubham, were you able to figure out the uh, dB per decade and dB per octave relation, or were you able to solve the assignment problem?
Yes, ma'am. I search from internet.
Mm-hmm.
So they given a factor called 10 dB per something 20 dB per decade is equal to 6. Wait, ma'am.
Okay. Let me tell you how that factor you are getting. So that is very simple. So in the previous class, I have given you clue also, hint to solve that problem. So what happens is, if you see, so what he asked was, what is the relation between dB per decade and dB per octave, right? This was your question.
Yes, ma'am.
So if any other student is interested, you can see this also. So let's suppose I'm just drawing a random thing. So here you have g of j omega magnitude in dB, and here you have your, so this is your Bode plot. Now how you define a slope? Slope is nothing but tan theta, if this is theta, or if I mark points here as y1, y2 and y3, and let's suppose this is um, omega, this is 2 omega, and this is 10 omega. Okay, so how you define slope?
Change of y divided by change of x, ma'am.
Okay, so let's pick points at omega and 10 omega, then it will be y1 minus y1 minus y3 divided by log of 10 omega minus log of omega, correct? So this will be equal to y1 minus y3 divided by log 10 omega by omega. So that is nothing but y1 minus y3 by log 10, and log 10 is 1. So the slope in dB per decade is nothing but change in y-axis, change in magnitude, okay, over a frequency change from omega to 10 omega. Okay, so this is your slope change or the magnitude change over a decade, and that is nothing but the slope of the Bode magnitude plot. Now this slope is also equal if I take points y2 minus y3 divided by log of 2 omega minus log omega. Okay, slope remains same. So what is it? It is y2 minus y3 divided by log 2, because you can write log 2 omega by omega, that will give you log 2. So what is this? Now tell me, uh, change in magnitude in dB in 1 decade, this is equal to how much? y1 minus y3. And what is change in magnitude in dB in one octave? It is y2 minus y3. And how y2 minus y3 related to y1 minus y3? These two are equal because slope are equal. So this must be equal to this, right? That means y2 minus y3 equals to log 2 times of y1 minus y3 we can write. That means change in magnitude in dB over one decade or this we can write as log 2 times of y1 minus y3. So what we can conclude is change in magnitude in dB in one octave is equal to log 2 times of change in magnitude in dB in one decade. So what is the conclusion? dB, so this is nothing but slope in dB per octave, and this is nothing but slope in dB per decade. So there is a relation of log 2 times of slope in dB per decade, right? So if anything which is given to you in dB per decade, you just have to multiply it with log 2. You will get the value in dB per octave. Okay, so in my previous last video, you must we had a question where we have converted 20 dB per decade, 20 dB per decade to be equal to 6 dB per octave. And how is it coming? So you multiply 20 dB with log 2. You will exactly get 6 dB per octave. Okay.
Yes, now clear.
Now is it clear?
Yes.
Okay. So just use a factor of log 2 to convert dB per decade to dB per octave.
Yes, ma'am.
Okay. Coming back to our question, what are the open loop poles? -4 and 1. Vignesh. Okay, so very basic. S square 3s minus 4. You can use the factorization. So it will be s plus 4. So the poles are 1 and -4. Okay.
Yes.
Okay, and what are the closed loop poles? First find out the closed loop characteristic equation and then calculate the poles.
Ma'am, show the question.
Okay, the transfer function was 3 into s plus 3 s square plus 3s minus 4. This was the open loop transfer function. So what will be closed loop transfer function? We have to just add the numerator and denominator, right? So this is our characteristic equation, which is s square plus 6s and 3 square 9 plus 5 equals to 0. So this is nothing but you can easily see you have factors x plus 5 plus 1. So the poles are minus 5 and minus 1. Okay. Okay, now you have your open loop poles and closed loop poles with you. So the question is, what can you conclude about the mapped contour of the Nyquist contour in the GSHS plane? So whether it will encircle the origin or it will encircle the minus 1 point once or twice, or in which direction, you have to tell me. Okay. So basically you have to tell me whether there will be any encirclement about the minus 1 point, obviously, because we are mapping to GSHS plane. If we were mapping to 1 plus GSHS plane, the encirclement we have to consider were about the origin. But we are interested in the GSHS plane. So the 0, the origin is shifted to minus 1 point. So the encirclement will be, if there is encirclement, it will be around the minus 1 point. So first question, so the last two options are not valid options because we are considering the GSHS plane. Okay. So the encirclement will be around minus 1 point. If we were asked about the 1 plus GSHS plane, then we have to consider encirclement about the origin. Okay. So it is specified that the encirclements we have to consider is in the GSHS plane. Now what does Nyquist stability criteria? So we know that number of encirclements is equal to Z minus P. And what is Z here?
Zero.
Zeros of what? So in Nyquist stability criteria, you just have to remember this relation and remember this relation very precisely. What does N denotes here? What is Z and P? Okay. So Z is closed loop poles in RHP, right? And what is P?
Open loop poles in
Yes,
RHP.
P is open loop pole in RHP. Okay. So this is the most important thing that you need to remember if you have any question on Nyquist plot or Nyquist stability criteria. Okay. Now, just now we have calculated the closed loop poles. What were the closed loop poles for this transfer function? It was at minus 5 and minus 1. Now, whether there is any closed loop pole on the RHP, both of these poles are located on the
LHP.
LHP. So, in our case, Z equals to 0. Okay, and what about P? Now let's look at open loop poles. So
One minute.
open loop pole were at 1 and -4. So there is any open loop pole on the RHP? Yes, there is one. At s equals to 1 we have a pole, and that is on the right half plane. So P is 1. Okay. Now calculate number of encirclements. It is Z minus P, which is equal to minus 1. That means how many encirclements we have?
One
One
counterclockwise.
encirclement.
One encirclements, and in which direction? We have
Counterclockwise.
negative sign, so that is counterclockwise direction. So the correct answer is option A. Any doubt? Okay, then let's move forward. Okay, so you are given a transfer function, right? And consider a unity negative feedback. Okay. In problem 1, let the transfer function be this. Considering unity negative feedback, one can infer that the controller structure is that of. Okay. So in problem 1, our transfer function was. Okay. So earlier, the transfer function which was given to you was. Problem 1 is this 3 into s plus 3 divided by s square plus 3s minus 4. Now your new transfer function is 3 by s square plus 3s minus 4.
Ma'am, this is plant function, ma'am. Plant into control is equal to total transfer function.
Yes, 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 yes. So, no, no, no. What you are saying?
Ma'am, that is the total transfer function, ma'am. This is only the plant transfer function.
And where what was given in problem 1?
3s plus 3 divided by x square plus
Okay, okay, okay. Yes, yes, yes. So your GSHS was this, and your plant transfer function is this. Correct, correct, correct. Where is the question? Yes. So this is your plant transfer function. So this is not new. This is your plant transfer function, right? And then your transfer function was this. Okay. So this, and you have a unity negative feedback. So this was your GS into system. So this was your GS into HS. Okay. And your GS is CS into PS into HS. And what is your CS? PS? It is this value. And HS is equal to 1 because it is a unity negative feedback. Then what is your controller? What is CS? If your PS is this, what can be your CS? The only factor which is extra is S plus 3. If you multiply S plus 3 with this value, you will get this. So what is your controller? Your controller is S plus 3. Okay. So this is your PS. And this is your CS. Okay, and these two are in series, so the transfer function will multiply, and so we can conclude that the controller transfer function is S plus 3. So what do you think? S plus 3 is what type of controller? If S plus 3 acts on something, what it will do? What is the property of S?
Differentiation.
It will differentiate. And what is 3? It will just a proportional constant. So this is a proportional derivative controller. So the correct option is D. Okay. Okay then. So in this question, it is said that consider a causal LTI system whose open loop transfer function has two poles in the RHP. So let's note down. We have open loop transfer function poles which are two in RHP. Okay, with the remaining poles in the left half complex plate. Okay, other poles of open loop transfer function are on the LHP. From the plot of open loop transfer functions contour corresponding to the Nyquist contour. So what is your Nyquist contour in the S plane? It is the semicircle of infinite radius, that is, it covers the RHP. Okay, so from the plot of the open loop transfer functions contour corresponding to the Nyquist contour, the corresponding negative feedback closed loop system will be stable only when. So this is nothing but Nyquist stability criteria asked in a what we can say very explanatory manner. Now what is asked here? You are given a Nyquist contour and it is mapped to GSHS plane. So this is nothing but the Nyquist stability criteria. You consider only about the RHP. So that's all this question is all about. And it is said that you have two open loop transfer function in RHP. Then for closed loop stability, which option should be correct? Now let's again recall what is Nyquist stability criteria. It is Z minus P, where Z represents closed loop poles at RHP and P represents open loop poles at RHP. Okay. Now what is the condition for closed loop stability? What we want? We want our closed loop poles to not lie in RHP. So what is the stability criteria? What we want? Which parameter should be 0? Z or P? For
ZP.
closed loop. So for closed loop stability, closed loop poles should not lie in RHP. Okay. So that means the condition is Z should be equal to 0. Right? So if you put Z equals to 0, you will get 0 minus P. And what is the value of P? It is already given that you have open loop poles at RHP equals to 2. It is given in the question. That means NC is equal to 0 minus 2, means NC equals to 2. What does it mean? Sorry, minus 2. What does it mean? How many encirclements we have? We should have for stability. We should have 2 encirclements, right? And in which direction?
Counterclockwise.
counterclockwise direction, and about origin or about -1 point?
About -1.
About -1, because it is given that uh, open loop transfer function contour corresponding to Nyquist contour. So we are considering open loop transfer function contour, not closed loop transfer function contours. That means encirclement about -1. So this is your GSHS plane. So the answer should be -1 twice in the counterclockwise direction. Clear to everyone?
Yes, ma'am.
Yes.
Okay. Now similar type of, so is it same question? Yes. Now here the similar type of question, but here you are given the open loop transfer function. Now you can use easily tell me. You are given a negative feedback closed loop system with open loop transfer function s minus 7 by s square plus 3s plus 2. Then one can conclude that the mapped contour of the Nyquist contour in GSHS plane will be what? So first calculate the open loop poles and closed loop poles at RHP and tell me whether there will be any encirclement or not. First calculate Z and calculate P. So for Z you need to calculate closed loop poles at RHP, and for P you have to calculate open loop poles at RHP. So for open loop poles you have to solve s square plus 3s plus 2 equals to 0, and for closed loop poles you have to solve s square plus 3s plus 2 plus s minus 7 equals to 0. So if you solve this, you will get 2s plus 1. So it will be s plus 2 and s plus 1. Okay. Open loop poles -2 -1 is correct. -1 and -2. So what will be P? Do we have any open loop poles at RHP? So P will be 0. Now what will be Z? Let's calculate it. It will be s square 4s plus 5. So this we have already calculated earlier also. It will be s, no, it will be -2. So it will be s plus 5 minus 1. So s will be equal to 1 and -5. Now we have closed loop poles at 1 and -5. That means z is equal to, we have only one closed loop pole at RHP, so z equals to 1. Now let's calculate number of encirclements. NC is nothing but z minus p, which is equal to 1 minus 0 equals to 1. So we are getting one encirclement
About -1 in clockwise direction.
in clockwise direction. D is the correct option. Okay, so you are given GSHS be the open loop transfer function of a negative feedback closed loop system, then the closeness of G omega H omega locus on the minus 1 point is indicative of relative stability, correct? Because if you draw the root locus or Nyquist plot or anything, so suppose this is your minus 1 point, so this indicates the point which crosses where the poles, closed loop poles crosses the imaginary axis. So the closer your locus is to minus 1 point, the more you are vulnerable to getting unstable, right? And the larger and the more away you are from minus 1 point, the less vulnerable you are getting to unstable. So that's why we uh, define relative stability with respect to closeness of the locus with minus 1 point, right? So this is how your relative stability is defined. Okay. So consider a unity negative feedback closed loop system with open loop transfer function as 2 divided by s square plus 3s. Calculate the gain crossover frequency. So we are asked to calculate the gain crossover frequency. First tell me what is gain crossover frequency?
Where phase cuts 180 degree.
No, gain crossover frequency.
Magnitude passes 0 dB.
Yes, so the frequency at which the magnitude of g j omega h omega equals to 1, or if we are talking about in dB, then your magnitude of gh in dB equals to 0 dB, right? So this is your gain crossover frequency. So for this transfer function, calculate the magnitude, put that equals to 1, and calculate at which frequency you will get the magnitude as 1, or if you calculate it in dB, at which frequency you are getting 0 dB. Both way you can calculate. Okay, let's solve it. So first we need to write our transfer function in j omega form. So that will be square 3j omega. That will be equal to minus omega square plus 3j omega. Okay. So what is the magnitude? Let's call it G. What is the magnitude? Will be 2
under root.
omega 4 plus 9 omega square, and that should be equal to 1. So let's square everything. It will be 4 equal to omega 4 plus 9 omega square. That means you need to solve omega 4 plus 9 omega square minus 4 equals to 0. So this is your fourth order equation. How can you solve it? Let omega square equals to let's call it alpha. So your alpha square plus 9 alpha minus 4 equals to 0. So this becomes your quadratic equation. Now can you calculate for alpha? So you,
0.424.
how much?
0.424. Another one is minus 9.42.
Minus 9.42. Okay. So your alpha will be minus 9 plus minus. Okay, so this will be your alpha. And when you calculate it, you will get alpha, one alpha as it will be minus 9.42 and another alpha as 0.424. Now, which alpha we should take? The positive one or the negative one? Remember that alpha equals to omega square. So alpha is representing the square of some real value. Okay, that means alpha can never be negative. So which value should we take?
0.424.
0.424. Now if you have alpha, then your omega will be under root of alpha. So omega will be omega.
0.651.
This you will get as 0.651 radian per second. So at this omega, the magnitude of the transfer function is equal to 1. Okay, so that's what omega GC represents. Now similarly, calculate the phase crossover frequency. Phase crossover frequency. What is phase crossover frequency? Frequency at which your phase of Gj omega h omega equals to minus 180. Okay. And why these gain crossover frequency and phase crossover frequency are so important for us? Why they are defined in this way only? Why it is defined like the magnitude should be 1 and phase should be minus 180 degree? From where it is coming?
Ma'am, because if it is not if it is not meeting this value, then the poles will transfer from the left of plane to the right of plane.
Yes, absolutely correct, because this represents the critical point in the Nyquist plot. Here you can see this is how the relative stability was defined. So this point minus 1 point represents your critical point. Okay, so we don't want our plot or our poles to fall at this point. So this is the critical point, and therefore we have characterized the frequencies based on this critical point, because this point represents magnitude of 1. Okay, magnitude of 1, and phase we have, or here from you can see it is minus 180 degree. So this point represents magnitude of 1 and phase of minus 180 degree. And since it is a plot of varying frequency, so that's why we have characterized this as gain crossover frequency and phase crossover frequency. Okay, please calculate the phase crossover frequency. Let me write the transfer function. It was problem 8, 2 by sorry, was transfer function was 2 by s into s plus 3. That is 2 divided by j omega plus 3. So what is the phase? What is phase of 2? It is 0 degree. What is phase of 1 by j omega?
90 degrees, ma'am.
But it is in denominator,
90 degrees.
so it is minus 90. And similarly, for this, we will have minus tan inverse of omega by 3. This should be equal to minus 80 degree. That means what should be omega such that uh, this becomes equal to minus 180 degree. So here I have drawn
Infinity, ma'am.
infinity, right? So here I have drawn the plot of tan inverse. Okay. Okay, so this is your argument. And from the plot of tan inverse, you can conclude that as this argument tends to infinity, your angle converges to 90 degree. So omega should be infinity for your phase to be equal to minus 180 degree. Okay. So your gain crossover frequency is infinity. Okay. Now calculate the
Ma'am,
phase margin. Yes.
I am confused about what is gain crossover margin. So please explain a little bit.
Okay. Margin you are asked. We have not solved any question of gain margin
This
yet.
recent question,
Okay, how we are
phase
getting
crossover
infinity?
margin.
How we are getting infinity is the question.
Oh, what is phase crossover
Okay, what is
Yes, yes.
phase
How
cross?
getting infinity?
Okay, so the definition of phase crossover frequency is nothing but the frequency at which the phase of open loop transfer function is equal to minus 180 degree. So this is as per definition. Now, based on that definition, we have calculated the phase. Okay, the transfer function was given to us. So, how can we write the phase of this transfer function? In many questions we have done. So, uh, the phase of numerator is taken as positive and the phase of denominator is taken as negative. That you all know. Then we have in numerator we have just a constant 2. So a constant of 2 means 0 degree, right? So this is 0. And what is j omega? J omega is your y-axis. That means that is an angle of 90 degree. Similarly, we have taken the phase for j omega plus 3, that is tan inverse of omega by 3. Now that should be equal to 180 degree. How can what omega can be to have an angle of so for that we need to have minus 90 degree kind of thing, then we can get an angle of minus 180 degree. And when tan inverse is gives you 90 degrees at infinity,
Tan inverse infinity.
so tan inverse infinity gives you what, 90 degree.
And suppose
Yes.
if you transfer 90 to other side, it becomes minus 270. And taking tan on both sides, you can get omega by 3L. Can we check like that?
What you are saying? If we take minus tan inverse omega by 3, then it becomes
270
90
minus
degree.
minus okay 90 degree, minus 90 degree.
And if you take tan inverse, it becomes minus 90. Anyhow, you will get same thing.
Yeah.
And tan inverse
Clear one.
is
Yeah.
minus 90 at infinity. So that's why the answer is infinity.
Clear.
Clear?
Yes.
Okay. Okay. Now, so we were at phase margin. Then how is phase margin defined? So what is the point of instability? The point of instability represents the phase of minus 180 degree. We have seen here the critical point is minus 1 and its phase is minus 180 degree. So how much phase lag needs to be added to the system such that the system becomes or system is brought to the verge of instability. So that's how your phase margin is defined. So gamma is, and if you see the Bode plot, from there you get this formula where your phase margin is nothing but the phase of your G omega H omega at gain crossover frequency minus of minus 180 degree. So how far you are from minus 180 degree, that much amount is added to the system and your system becomes unstable. So this quantity represents how far you are from the minus 180 degree when your magnitude equals to 1. Okay, so when your magnitude is equals to 1 means that you are calculating thing at gain crossover frequency and how much at that frequency you are away from minus 180 degrees. So that's how your phase margin is defined. Okay, so as per definition, this is your formula. So you have to calculate first the gain crossover frequency. So first calculate gain crossover frequency, then calculate phase add gain crossover frequency, then calculate gamma. So gain crossover frequency we have already calculated in our previous question. And how much was that?
0.65, ma'am.
So omega GC was 0.65. And what was the phase of G of J omega H omega? So for that we need transfer function. What was our transfer function? It was 2 by s into s plus 3. Okay, so your G of J omega H omega was 2 by J omega 3 plus J omega. Okay, so what is the phase? Just now we have written it is minus 90 minus tan inverse of point so omega GC divided by 3. Okay, so we need to calculate at 0.65, so it is tan inverse 0.65 divided by 3. How much you will get?
Not 2.2.
Yes.
Well, not 2.2, man.
Okay. So you will get minus 90 minus it will be
12.2.
12.2 degrees. That means your phase margin is it will be minus 102.2, correct?
Yes, ma'am.
Yes.
So no, so this is not your phase margin, this is your phase at gain crossover frequency. Now third step is calculate gamma. It is angle of g j omega h j omega at omega equals to omega gc, and minus minus will become plus, so it is plus 180 degrees. So here the formula is minus of minus 180. So in short you can write plus 180. Okay, it becomes minus 102.2 plus 180. That
77.2.
okay, so it is 77.77 degrees.
78.
That means if you draw the phase plot, let's suppose this is your minus 180-degree line. So your phase plot will be such that you have, if you are at 0 dB frequency is this. So suppose your magnitude plot is such that you are getting at omega equals to omega gc. This is your 0 dB line, and at this frequency you have calculated phase. This phase you are getting was minus 102.2 degrees. So 77.77 degree you are far away from minus 180 degree. So that's what your phase margin means. Okay, so what we calculated, these are same questions. Okay, I have repeated the question. Now calculate the gain margin. So the definition of gain margin goes the same way as the definition for phase margin. So how should we define gain margin? How much gain should be given to the system at phase crossover frequency such that the magnitude becomes 1, or if you are talking in dB, the magnitude becomes 0 dB. Okay, so when your magnitude, so suppose you have your g of j omega h of j omega, right, and you are calculating at phase crossover frequency, how much gain should we multiply to this magnitude so that this becomes 1? That's all we want now. What should we multiply, or how much gain should we give to the system at phase crossover frequency such that its magnitude becomes 1? If we just multiply with its reciprocal, right, these will cancel and will give you 1. Okay, so that's how gain margin is defined. So gain margin is nothing but 1 divided by magnitude of g omega h omega at phase crossover frequency. Because if this much amount of gain is added to the system, you will come at the verge of instability. Your gain will become equal to 1, right? So we have to follow the similar steps. First, calculate phase crossover frequency. Second, calculate magnitude of g j omega h omega at omega is equal to phase crossover frequency. And third is calculate reciprocal of g omega h omega. Okay, follow these steps and calculate. So your transfer function was 2 divided by s into s plus 3. You can calculate this question orally. You need not to calculate anything because what was your phase crossover frequency? It was infinity. Now put infinity in this transfer function. What you will get? 1 by infinity is 0. So the magnitude is 0. And you have to calculate its reciprocal. Reciprocal of 0 is 1 by 0. That is infinite. So the answer is
Option D, ma'am.
option D. Okay. So what does it mean? It means that system is such that it is never ever going to have magnitude of 1. Whatever frequency you put into the system, whatever frequency you have the system, it is never going to touch the magnitude of 1. Okay, you have an infinite gain margin. Okay. Okay, this question has asked about the closed loop pose corresponding to the open loop. So this is just a very basic question. You have to calculate the closed loop pose. And in your problem 8, the transfer function was, okay, the same transfer function. Find out the closed loop pose of 2 divided by s into s plus 3. It's a very simple one. So the open loop poles are at 0 and minus 3. The closed loop poles will be s square plus 3s plus 2. So by looking at here, you can conclude that you have poles both in the LHP.
-1, -2.
Yes, 2 minus 1 minus 2. Very simple. Okay, now for the same transfer function, that is 2 by s into s plus 3, calculate the cutoff frequency. Oh no, sorry. The question is something else. Okay, sorry. You have to calculate the low frequency value of its magnitude in dB. So what does it mean? Low frequency asymptote you have to calculate for this transfer function in dB. The low frequency value. So calculate the magnitude in dB. Put omega tends to 0 and tell me the magnitude. So it is asked for closed loop, not open loop. the magnitude at low frequency in dB of the closed loop transfer function. Three by s into s plus c is your open loop transfer function. So the closed loop transfer function is sorry. This is
It's 2 by 9.
yes 2 3s plus 2. Okay. So j omega it will be 2 minus omega square plus 3j omega plus 2. So the real part is 2 minus omega square and plus 3j omega. So magnitude in dB, how can we calculate? It is nothing but 20 log of 2 divided by 2 minus omega square whole square and plus 9 omega square. Okay. So this we can write as 20 log 2 and okay. Put omega tends to 0. It's very simple. You will be left with 20 log 2. If omega is 0, this goes to 0, this goes to 0. So you will be left with under root 2 square. That means 20 log 2 by 2. That means 20 log 1 is 0 dB. Okay. So at low frequency, its magnitude in dB is 0. That means if you draw the body of the closed loop transfer function, that is g by 1 plus g, whatever low frequency you are taking, it will start from 0 dB. Okay. Because this thing we need to calculate question which is related to cutoff frequency. Okay. So the cutoff frequency is calculated at the in value of the closed loop transfer function at the initial frequency, not at the initial frequency, 3 dB lower to the initial frequency value. That magnitude gives you the cutoff frequency. So if the initial frequency value is 0 dB, so you just have to calculate the magnitude at 3 dB. So that's how things become easier when the initial frequency magnitude is 0 dB, right? So here in this question we have calculated that the initial frequency magnitude is 0 dB. Now see what next question is asked. Okay, the slope in dB per octave of high frequency asymptote is equal to. So you have to calculate the high frequency asymptote in dB per octave. Remember that you are asked about closed loop, not open loop. So you have to consider the transfer function s square plus 3s plus 2. So for this you can easily tell me how many poles we have. We have two poles. So what will be the high frequency asymptote? We have two poles, so we will have minus 40 dB per decade, because one pole contribute for minus 20 dB, another pole will contribute for minus 20 dB. So at omega tends to infinity, your overall slope as omega tends to infinity will be minus 20 minus 20, which gives you minus 40 dB per decade. You can calculate by calculating the magnitude and then putting omega tends to infinity also. But with experience, we know that since we have two poles, that means as omega tends to infinity, we will have minus 40 dB of per decade asymptote. Okay. So if you have minus 40 dB in per decade, how much will it be in octave? You just have to multiply minus 40 with log 2. Tell me how much is it?
minus 12 octave.
It is minus 12 dB per octave. Okay. Now the last question. Calculate the cutoff frequency of the closed loop transfer function. So just now I have told you what is cutoff frequency. So in the magnitude plot of the closed loop transfer function, take the initial frequency, take the magnitude. Suppose uh, suppose this is your magnitude Bode plot, and at initial frequency, whatever is the value is, you have to go below by 3 dB. Okay, so this will be the magnitude. You started with initial frequency magnitude, you come lower by 3 dB, and then you look for the frequency corresponding to that magnitude. So for this particular transfer function, you hit this value, then corresponding to this value is your cutoff frequency. So this is how the cutoff frequency is defined. Now for this problem, we have calculated that the initial frequency, that means as omega tends to 0, what was the initial magnitude? It was 0 dB, right? So you have to calculate the frequency at which the magnitude of the closed loop transfer function is minus 3 dB. So because if you come 3 dB lower to 0 dB, means you are at minus 3 dB, correct? So calculate the magnitude of the closed loop transfer function, make it equal to minus 3 dB, and calculate the corresponding frequency. That will give you the cutoff frequency. So your closed loop transfer function was 2 by s square 3s plus 2, and in j omega we have calculated as 2 by omega square 2 minus omega square plus 3 j omega, right? Calculate its magnitude. So we have 2 for cutoff frequency. We have to calculate the magnitude of g of j omega closed loop transfer function. I am writing magnitude in dB. That should be equal to, for our case, that should be equal to minus 3. Okay. So this is equal to 20 log 2 divided by 2 minus omega square whole square and plus 9 square. This should be equal to minus 3. So log of minus 3 by 20, you can calculate 2 divided by 2 minus omega square whole square plus 9 square equals to 10 to the power minus 3 by 20. Okay. What value you will get? 10 to the power is minus 3 divided by 20. It is 0.7079, so you can take 8. Okay, now you can square both sides to simplify it. So when you square it will be, let's square it. So to square it you will get 0.501. So 4 by 2 minus omega square whole square plus 9 omega square equals to 0.5. It is 0.5 into 0.5 you can take. You have 0, 1. So ultimately what you will get is so this you can approximate as omega 4 this you will get as 8.16, which you can approximate as 8, and then you can solve this quadratic equation, which you will get as approximately omega 4 plus 5 omega square and 4 2 square 4, so 8 minus 4 will be 4, so minus 4 equals to 0. So this quadratic, if you solve, you will get omega square equals to, again by putting alpha you can calculate. So one you will get 5.7 and another you will get 0.701. So negative we cannot take. So omega square equals to 0.701. That means omega is square root of 0.701, that is equal to 0.837 radian per second. So you can do the calculation thing. So first is the correct option. Okay. So for such type of question you have to be very quick in calculation thing. If it is asked in gate you have to be very quick. Alright, we have some time left. We can solve one or two more problems. Okay, let's solve one problem related to this topic only. We will solve one more problem, then we will end this session. Okay. Okay, in this question, you are given a table where you are given the magnitude and the phase of the open loop transfer function. Okay, And what are those values? So, okay. So you are given magnitude of G and angle of G. Okay. At 1.3, your phase is minus 130. At 1.2, the phase is minus 140. At 1, the phase is minus 150. At point 8, the phase is minus 160. Similarly, at point 5, you have a phase of minus 180. It is in degrees. And at point 3, it is 200 degrees. So the magnitude is given, but it is not given in dB. Okay, it is just a magnitude. It is not in dB, and the angle is given in degrees. You have to calculate gain margin and phase margin. The options are 6 dB and 30 degree, 6 dB and minus 30 degrees, minus 6 dB and 30 degrees. The last one is minus 6 dB and minus 30 degrees. So if you remember the definition of gain margin and phase margin, by looking at this data, you can calculate what is the phase margin and what is the gain margin. How is gain margin defined? The gain that should be given to the system at phase crossover frequency such that its magnitude becomes equal to 1. Okay, so first we have to look for the phase crossover frequency, but the frequency is not given to us. Instead, we are given the magnitude and phases. So the phase of interest for gain margin is the phase crossover frequency. Okay, the frequency at which phase is minus 180 degrees. So by looking at this table, we have a phase of minus 180 degree given to us. Okay, we have a phase of minus 180 degrees given to us, and at this phase, how much is the magnitude? The magnitude is 0.5. Okay, so how much more magnitude we can add to the system such that the magnitude becomes equal to 1, because this is not in dB, so we have to consider magnitude equals to 1. If it were in dB, we have to consider magnitude equals to 0 dB. So how much more gain should we add to 0.05 such that it becomes equal to 1? Sorry, such that it becomes equal to uh, dB. Let me check if it is given in dB or magnitude. So it is
Option A, madam.
Yes. Option A, but there is, I think, some sign problem is here. So if it is, just give me some time, I will check it. Okay. Okay, so this is not in dB, so that's what I was checking. Okay, so we at the angle of minus 180 degree, we have a gain of 0.5. Okay, and how is the gain margin is defined? Gain margin is just the reciprocal of the magnitude at frequency where the phase is minus 180 degrees. Okay, so that magnitude it is given to us. So what is should be the gain margin? Is it is just the reciprocal of 0.5. That means equals to 2. Now if we want to calculate in dB, it will be just 20 log 2. So 20 log 2 is nothing but approximately equals to 6 dB. Correct? So the gain margin is 6 dB. And what is then the phase margin? How is phase margin defined? It is how much phase lag should be given to the system at gain crossover frequency such that its phase becomes equal to minus 180 degrees. So the frequency of interest is at magnitude where the magnitude is equals to 1. If it were given in dB, so we have to check the phase at which the magnitude is 0 dB, but since it is not given in dB, we have to check the phase at magnitude of 1. So at 1, what we have? The phase is at minus 150. So the phase margin, that is gamma, is the angle of g omega h omega at gain crossover frequency plus 180 degrees, and this value is given to us, which is minus 150 and plus 180, so that is equal to 30 degrees. The correct option is A. Alright.
Yes, ma'am.
Okay, so similar to this type of question we have some more question, but let's stop here. We will take these questions in the next session, that in the next week.
Thank you.
Yes, any doubt?
No, madam, sir. Thanks.
Okay.
Thank you.
Okay, so next week will be the last session of the problem solving session. We will have one extra session where we will take MATLAB problems or solves these type of question using MATLAB. And if you have any other doubt, you can also ask in the extra session that will be announced in the group to you. So for the next session, we will have questions on compensator design, and we can take some more questions on Nyquist also, because I think some more questions need to be solved to have further clarification. So we'll take some more question on Nyquist and compensator design, and in the extra session we will have some MATLAB problems. Okay. So if you have any question, you can ask, or we will meet next week. Thank you.
Bye, man.
Bye bye.